Hello class, today I'm going to show you how we can do mesh dependency test. When we are doing simulation using Fluent, one of the steps is defining mesh, and usually we keep using very coarse mesh, but usually if you want to have much more accurate and trustable result, you need to refine mesh. But the biggest question would be up to what extent you need to refine your mesh. So I'm going to answer that question. This is going to be one of the procedures or steps you're supposed to do for any simulations. So you can't report any simulation without doing mesh dependency test. For this simulation, I'm going to make everything simpler. It is going to be 2D case for a 90-degree bended pipe, and it is going to be steady state. So no time dependency, just we're going to focus on mesh size. So let's open Fluent, and now I want to specify I would like to have a 2D case, not 3D. So right click over geometry, open properties, and now you can have this. Analysis type, I'm going to select 2D, so answers from beginning is going to know, okay, it is going to be 2D. Double click over geometry to open space claim, and we are going to draw our simple geometry. I'm going to have turbulent flow, so the sizes, everything I'm considering is going to be for adjusting for turbulent flow. So let me change the units to 0.1 meter. So let's draw it. This one I want to have 6 meter, and then 1 meter here, five meters here, and then let's have 10 meters, 1 meter, and done with the geometry. Now you can see this is our 2D geometry. This is curves. As you know, you need to convert it to the surface. To convert it to surface, you select all curves and fill it. Now it is 2D case. Let's close this and open our mesh. Okay. Okay, mesh is ready. Let me name it. So select edge selector. This is going to be my inlet. Right click, name selection, inlet. This side is going to be my outlet, and all other sides are going to be my wall. Right click, name selection, walls. So this is a pipe, 90 degree, very sharp. Inlet is going to be here, 0.1 meter per second, and outlet is going to be pressure outlet. For the mesh, I'm going to adjust mesh with this maximum face size. So starting point is going to be 0.5 meter. So let's generate. This is 0.5 meter mesh, and these are my name selections. just want to make sure I have it. So for this mesh, the element size is 0.5, and the number of mesh is just 64 elements. I prepared this Excel sheet for this case. So elements number was 64 and size was 0.5 meter. Later I'm going to show you what are these other parameters and how I can find them. So the first case. Okay, I'm just minimizing because I'm going to come back and gradually refine mesh. Update our mesh and open our setup. Okay, Fluent is loading our geometry. Because this is 2D case, as you can see, this says 2D space planner, and we are happy with this. For the model, as I said, I'm going to have 0.1 meter per second here, diameter is 1, and the fluid is air. If you calculate Reynolds number, which is velocity times diameter divided by kinematic viscosity, it is going to be about 6,800, which is turbulent flow. So I'm changing viscous from laminar to K epsilon model. Later I'm going to explain what are these models, what is RANS, what is LAS, and what are the basics about those models. Okay, for now just follow my steps. So we selected turbulent flow, which is part of the RANS models. For the materials, I'm happy with the air, and you can see the information about the density and viscosity which you needed for your Reynolds calculation. Just make sure cell zone, this is going to be fluid, and fluid is the only fluid we selected is air, so it is going to be air. Let him put the boundary conditions. Inlet, it's velocity inlet, so the magnitude is going to be 0.1 meter per second. Happy with it. For the outlet, pressure outlet, done, and walls, it is going to be wall. I don't need to change anything. Let's go and initialize it. Hybrid initialization, and run the simulation for example, 500 iteration. This is steady state, so 500 probably is going to be enough. Let's go back and open results. Okay, contours, let's see, velocity, for example 50 at symmetry 1, and you can see this is our velocity. High velocity at center and lower velocity close to the side walls, and this is like this. We know that close to the walls we have no slip condition, so velocity should gradually close till reaching 0. So this part is okay, but the others, maybe they're not that much accurate we want. I would like to define 2 points here. First of all, for the pipe calculations, usually pressure drop is an important factor, and we have a lot of empirical equations. You can use that if you remember from fluid mechanics, Moody diagrams to find pressure drops. So I'm interested in pressure drop inside this. If it was like a temperature involved there, I may select temperature as a monitoring point. So let's see pressure here. This is the pressure, higher pressure there, and lower pressure this side. So I would like to define 2 points as a monitoring points to find pressure drop because of this L-shape pipe. So point 1 is going to be x 0.5 y 5. Let's apply. So this is the first point, and second point is going to be around here. So y is going to be 0.5 and x is going to be 9. Let's see. 10, for example. So 1 meter to the outlet, here 1 meter to the inlet. Let me check. It was 5. Yeah, overall it was 6 meters, so I put it 5 there. So let's read the pressure there. So if I select this, I can see what is the pressure at this point. So let me copy this, and this is my pressure at, okay, I couldn't copy, so I'm going to write it. Negative 8.94073 E negative 6. Okay. What about the other point? This point is going to be point 00793356, and the pressure drop is going to be the difference between those two. Done. And what is y plus? Okay, as you can see here, we have a bended pipe here, but usually close to the wall we have more temperature gradient or velocity gradient or pressure gradient. As you can see here and here, we have sharp change in our parameters. So to quantify how accurate the results close to the walls are, we define a new parameter. We call it y plus, which is kind of showing how many mesh we have there inside that closed area, inside the boundary layer of the wall, which is usually if it's a turbulent flow, it is going to be very thin. So that y plus is going to show us how accurate and how many mesh we have there to capture the behavior. Let me show you something here. This is the figure. This figure shows the y plus as the x axis and velocity as y axis for the turbulent flow. As you can see, if your y plus close to the wall was, for example, 1000, you're not going to capture this velocity gradient close to the wall. So your y plus should decrease to capture these behaviors close to the wall. For example, if it's less than, for example, 5, 6, you are going to have better, you can capture more details of the your parameter close to the wall. So we usually refine our mesh close to the walls or close to the area we have sharp change to capture more details. Okay. Let me check velocity again here. This is the velocity profile. But we don't, as we know, the physics of this type of flow inside L-shape pipe shouldn't be like this. Let me show you what we should have expect of this type of flow. So we should have some circulations here, or zero velocity here, and these two sides for the sharp change of the pipe direction. So here we couldn't capture that, so we expect to see some differences here. Okay, let me close that one and go back here. I also would like to check the y plus, because I input everything except y plus, so I'm bringing xy plot here. Inside our turbulence, we have wall y plus over walls, not outlet, over walls, and we can check what is the magnitude. It's 20, around 128. So let me put 128 for y plus for this mesh size. Okay, now I'm going back to my mesh size. It was 0.5 meter. Now let's go make it 0.2. Remember, usually we refine mesh 50%. Here sometimes 100%, depends on the results we are getting. So here I put 0.2, generate mesh. We are going to have a little bit finer mesh, as you can see. I'm updating it. Let's minimize, go back here, update setup. Yeah, we need to wait to have this green check there. So I'm back here. The only thing I need to do is initialize it again. And this is the final mesh, as you can see here. And let's run it. This time it is going to be a little bit longer time, but done. Still, we don't have that many mesh. I forget to write the number of mesh. We have 400 elements and the size is 0.2. Let me enter here. 400 elements, 0.2 is the largest size, and I need to read the rest. Okay, our result is ready. Let me go back, update. And open the results. Now you can see a bit more details. We can see that zero velocity area, some circulation may be happening here and here, which we expected. Now we can see there are more details and the results are closer to the experiments. Okay, so for point, let me turn off this. For point, this one is going to be, let me input the pressure value, which is a very small number, 4.6038 for E negative 5, and for this one pressure is 0.00707809, and this is the pressure drop. Okay, let's check the contour, which is closer to the picture I showed you here. We have zero velocity or circulation here. If you can't see circulation, I can show you vector from inlet. Turn off this. Symmetry 1. Apply. Symbol. size maybe 3. One. Okay. Yeah, this is the vector, so you can see we have less velocity there. Okay, let me close this. Oh, I need to find y plus for this case. Where are you? Here. So again, xy plot, pressure, turbulent, y plus for the wall, find it. It is going to be about 68. Yeah, 68. 68. So you can see a lot of improvement just from changing size from 0.5 to 0.2. Let's change the size to 0.1 this time. Okay, now I'm opening the mesh. Where is it? Here, 2.1, enter, generate mesh, update mesh, minimize, and let's update setup and the rest. Okay, setup is ready. Now you can see we have finer mesh there. Let's initialize it and run. Okay, simulation is complete. The first one I'm looking for is y plus for the wall. This time is 37. So y plus this time is 37. Let me check the number of elements we had. 1600. 1600. And for P1 and P2, I'm going to update this to have all the new results inside and open it. Now you can see circulation happens here. For the previous one, we couldn't see that much, but now you can see circulation. For the previous one, just one-sided flow. So let me turn on this. Now you can see we have circulations here and here. But the one we are going to check is those monitoring points. They are very important for us to do mesh independency test. Let me open this. So for point number 2, it is going to be 6.7. For 8 to 6, E -5. And for this one, pressure is going to be that. 0.007 to 8152 Pascal. And this is a pressure difference. Okay, next size, 0.005. Let me close this. Where are you? Here. From 0.1, I'm going to improve 50%, which is normal procedure. Usually we improve 50%. So we made the size half, and let me just check the number. 6,400, 6,400, And okay, let me update this, and then I need to update setup to make sure the information for the mesh is going to be transferred to the third part. Yeah, it's ready. Now you can see our finer mesh there. Let's initialize it. Ready, and then run the calculation. We have a little bit trouble here converging, but it's okay. XY plot to see y plus value close to the walls. This time it is 21. Y plus is going to be 21, and let me update the results here. And open it. Okay, we're happy. Okay. Now you can see more circulations here, and even this time at the lower part. Okay, let me turn off this and check the value for those two important points. It is 7.63821 E negative 5, and the other point is going to be 0.0080565, and the difference, pressure drop. Let's go further. 0.003 this time. Generate mesh. Each time it is going to be take a bit longer. Okay, it's ready. So the number is 17,606. 17,606. Let me update before forgetting it. And then open here, update setup, get the information in. Okay, green check is there. Now you can see we have much more finer mesh there. Let's initialize it and run the calculation. Okay, simulation is ready. Before moving to the other side, I just want to make sure I'm getting the Y plus over the wall, and this time it's almost 14. Let's go with 14. 14, and let me update the results here. double click. Okay, let's check the counter. Yeah, now you can see much more details. At lower resolutions, you saw this area was just blue and blue. Now you can see now there's a circulations, and we have a much more finer area close to here, close to the wall 0, but we have some circulations like this. Okay, now let's go and check the data for the monitoring points. Okay, this is a bit larger, but yeah, 0.30, 123, 155, and for the other one, 0.008, 40, 89, 5, and then this is the one. Okay, let's go further. 0.002 this time. 0.002, generate mesh. Okay, the new mesh is ready. The size was 0.02 and the number is 40,000. Let me add 40,000. Update this. Go back to the setup. Update this one. If you forget updating this, the information inside Fluent is going to be from previous mesh size. So make sure you're updating that. Let me close this. Now you can see the mesh size is much more finer now. Initialize it and run the simulation. Okay, simulation is ready. Let's check Y plus and then go find our monitoring points value. This time it's about 10. Yeah, let's go with 10. And update the results. And open it. Let me check the velocity counter. As you can see, now you're getting more results, and the zero velocity area close to the wall is getting thinner and thinner because the flow is turbulent and the boundary layers are supposed to be very thin. If you add a very coarse mesh, you're not going to capture those areas. Okay, so let's go back to our monitoring points and read those pressures. 000, 18, 10, 27 Pascal, and for the other one point is going to be 0.00819, and the pressure difference is going to be this. Okay, now let's draw a graph for elements, number and pressure. Okay, as you can see at the beginning, by increasing mesh the element numbers, we have a sharp changing in our results. But gradually, the results are going to converge to this value. If the difference between, for example, last two values was less than 2-3%, depends on your problem and your tolerance criteria, you can say, okay, these two, the difference is very small, or between these two, very small. So I'm going to select this one as a mesh size. So number 4, or for example, this one is going to be my mesh size. Or between these two is the difference is very low. So I'm selecting this one, which is number 5. So 0.03 is going to be my mesh size. And the results, you can say the results, if you refine mesh further, the result is going to be independent of the mesh size. Here you can say the results are dependent on the mesh size, but here you may say no, they're not that much dependent on the mesh size. Okay, or you can consider, instead of element numbers, y plus. As you decrease y plus and have a finer mesh close to the wall, you can see the changes are decreasing, and this area is the area you have less pressure drop change there. So you may say, okay, if the y plus was less than, for example, 10, I'm happy with it because the change of the pressure drop is much smaller. Usually people prefer y plus, and if you're working like a steady state flow, you may use just monitoring points, element numbers and monitoring points, and you can use this too. So it is your decision. I hope you learned something new, and see you next time.